So today we will see the last subject of the course, digital to analog converters and analog to digital converters. This is an important subject, and then we cover it in terms of digital electronics course. As you know, the signal in the environment in the world is in the analog format. Analog signals are there, but in order to process these subjects, we need to convert them to digital formats, so ones and zeros, as you know, and then but if we want to reconstruct it, then we need to use digital to analog converters to get an analog output. So this is the general concept. So for this thing, the analog signals needs to be converted to digital using analog to digital converters, ADCs. And in the digital domain, either we store it, efficiently, or we can do signal processing and then, after that stored data, for example, we try to convert to analog output. So this could be, let's say, a music signal or a sine wave signal or something, whatever we want to, convert that. So in the digital domain, we need to do a representation of these signals. Why do we need to do signal processing in digital domain? Because it might be, for example, cheaper or easier. There are all these processing power right now. All these things are going to be done in the digital domain. So the signal, we just use here a sample signal, let's say a sine wave. How can we represent that sine wave in the digital domain? So we split that signal, let's say maximum and minimum signal range, into digital representations, and then say that the lowest signal is going to be 0, 0, for example. This is if we have 2-bit representation. 2-bit representation will allow us a voltage level of 2 to the power 2, then it means 4. So the signal, the maximum signal, is divided into 4 parts, and then let's say the lowest signal is going to be 0, 0, the highest signal is going to be 1, 1, and then in between we give 0, 1, 1, 0 signals. Of course, this is not going to be a nice representation of that sine wave. And when we reconstruct that in the analog output, for example, in the analog domain, this is not going to be really good, nicely representing our signal, but it is going to be roughly representing, and then maybe we can do some filters and then, get rid of those sharp transitions, and then, get the signal again close to sine wave, but there's going to be loss of signal. So if we try to better represent that, maybe we can use 3-bit representation of that sine wave or that signal range. So this doesn't have to be, of course, sine wave, the signal, input signal, but this is for simplicity. We are showing a sine wave, how we can represent it. And again, for 3-bit, this is going to be 2 to the power 3, different voltages. We can split that maximum peak-to-peak voltage. And then the lowest is going to be 0, 0, 0, and then the highest voltage can be represented with 1, 1, 1. As you see now, this is maybe closer to sine wave looking digitized signal. So what is that blue? Blue is, once we connect that, convert that analog signal to digital signal, and then after that we use digital to analog converter to reconstruct that signal. So after the digital to analog conversion, the blue color is going to be obtained. It is obvious then that if we do this with more bits representation on the right hand side in the figure, this is going to be even better. So we can truly maybe represent that signal. So the higher the bits that we use is going to be the better. And and at the end, again, like we can use maybe some filters to smooth out that signal, so it looks more like a sine wave at the end. So this is the general concept, why we need A to D converters and D to A converters. So here, I mean, the bit number of bits, is it going to be 3 or 5 or 8? For some cases, this representation signal can be as high as 14-bit, for example. Think about a music that you are trying to record, so you want to be able to record that, as precise as possible. So sometimes like 8-bit will be enough, but for music recordings, maybe 14-bit or even 16 to 20 bits is considered. So making it more bits is going to be, of course, expensive, and then it will be consuming a lot of digital memory storage. So therefore this is going to be difficult, but it depends on what you really want. A better performance can be achieved. By the way, the pen arrived, so wow, my wife was very fast. So this is going to be maybe cheaper, easier, and digital signal processing plus storage. So here, in the examples that we will be talking, although maybe can be 12-bit or 18-bit, so this is difficult for us to explain. For simplicity, we use a 3-bit representation example. So for let's say 3-bit representation of a signal, 3 bits. Let's say this is 3-bit. Okay, signal. So here, this bit is going to be called as, let's say, A0. This is going to be A1. And this is going to be A2. Okay. So we say this is 3-bit. 3 is the resolution of this A to D. So how do we use this one? Resolution is number of bits. Okay, so this is the resolution. Of course, higher resolution is better. Okay. So too much resolution is unnecessarily high is not good. Okay. So good enough resolution needs to be selected as preferred. Okay. Too much is going to take a lot of area, because making that, you know, more resolution is going to be more difficult, of course. So you know, here we will be representing this like that, but we will be calling this bit representation as the least significant bit. Okay, so least significant bit, I mean A0, we will call this least significant bit. And then this one is going to be called most significant bit. Okay, so A2. So, I mean, we are introducing you to the definitions. So here, the smallest, least significant bit is going to be called also smallest voltage change among all the bits. So least significant bits, all the bits. Least significant bit is going to be, you know, like how much there's going to be voltage change here, the minimum amount of voltage change. Okay, so this is going to be the voltage-wise amount of that. I mean, least significant bit is the bit here, but voltage of LSB, or LSB, least significant bit, is going to be how much it is the smallest voltage. V full scale voltage divided by 2 to the power n. What is n? N is this resolution. Okay, so we call resolution as n. So this voltage is called V least significant bit. Okay, so the voltage of that amount. So you know, if the resolution is more, of course, V least significant bit is going to be smaller voltage. So n increases, then VLSB is going to be reduced. Okay, so for this case, this is going to be, you know, V full scale divided by 8, for example. So most significant bit voltage is going to be, you know, V most significant bit. How much it affects the voltage? It's going to be V full scale divided by 2 to the power n times 2 to the power n minus 1. So this is going to be most significant bit. Actually, it is always V full scale divided by 2. So this is the way that we define, and here typically we call this one 0, and then this one is the most significant bit, let's say 2 for this case. Okay. So you know, here how many steps we have in the 3 bits means here number of steps is going to be 2 to the power 3, or 2 to the power in general n. Okay, so if this is called V full scale, voltage full scale. So in summary, we have to represent that voltage in terms of digital bits, and then, you know, how many bits you decide to use is going to be up to you. Of course, the higher bits are going to be better in terms of precision, but it's going to be more costly. So, I mean, typically we use 8 maybe, or 14 or something in that range. So like, how can we define a voltage and find digital representation of a voltage? So typically we reference voltage is used for these devices, and then we call this reference voltage V full scale, typically. I mean, because sometimes you know, we take that voltage maybe different, slightly different. Okay, so full scale voltage, V full scale. Okay, so in this example, let's say this device is 10 bits. Okay, just to get you, you know, familiar with the subject. So now we want to have a digital representation A to D converter, okay, 10 bits. So how can we represent that signal in 10-bit resolution? So if the voltage that we want to convert is between 0 volt and 4 volt, and then this is the input to here, 3 volt, okay? So the how can we find that voltage representation? And typically, what you do is you take that input voltage, divide by the reference, and then multiply by this digital representation, because the maximum representation is going to be, you know, 2 to the power n. So if you have V in is 0, of course, digital representation is going to be, you know, 1, 1, or 0, 0, 0, 0, 0, 0, 10 times 0, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So what about if V in is 4 volts? Then this is going to be 1, 1, 1, 1. Okay. So 3 volt is going to be something in between. And typically what we do is we take that signal and then find you know, how much of that percentage wise of the full scale. So with respect to reference, what it is, and then multiply that by 2 to the power n. So if this n was 3, then it would be 8, you know, this number. But if it is 10, then it's going to be 1024. So if we do that and multiply it, it's going to be 768. So 768 then needs to be written in this domain. So how do we write this? You know that this 0 is 0, 0, 0, 0, 0, and this one is 1, 1, 1, 1, 1, 1. Okay. So therefore, we just need to write that in digital domain in a format like A9, A8, A1, A0. Okay. So the least significant bit and most significant bit. Okay. So I mean, how can we write that? I mean, we know that it should be at least, you know, this should be 1. I mean, so I'm not going to try to find that out right now. I don't have it, the value, but we know that the last digit should be 0 because it is 8 is not an odd number. It's an even number, so it should be last, or should be this value. Okay. So this is how we write the voltage. So this is going to be what is the value in terms of logic. So this is going to be 2 to the power 0, and then this is going to be 2 to the power 9. Okay, sorry. So this is going to be 512. Okay, so this is going to be, you know, weight of this is 1. So how can we find the last digit? The last digit, 2 to the power 8, is going to be 256, the weight of it. Okay, so if I take that, I mean, 768, and then now I used 1, so 512 is subtracted. This is going to be this one, 5, and then what is left here? What is left? 2. Okay, so that's simple then. This is going to be 1 here, and all the rest is going to be 0. Okay, so this was an easy one. Okay, so that's how we represent that signal. So because this was maybe a nicely selected number. So this is going to be then the output of, so this is going to be A9, this is going to be A0 output. And that's how we write. So we can do the other way around. So let's say we already have digital inputs. So let's say this is digital input. And then, you know, we have here, let's say, you know, code of 555. So digital representation of 555. Of course, you know, this is going to be 512. So is the first one. So in terms of logic, this is going to be something that may be 1. Okay, there are 1s and 0s, but this is the digital representation. This is the quantitative representation of that digital signal. So ADC code is 555 among 0 to 200, this one. So we divide that to this one and then multiply it with the reference. So now this is 10-bit digital to analog converter. And then, you know, this is going to be your output voltage here. Analog output is going to be this much. Okay, so so we need to make devices to that allows us to do these kind of conversions. That's this is A9, this is A0. Okay. So now I hope you got the idea about these devices. You know, we typically have VREF connected. So if VREF changes, then you know your analog representation will be changing at this signal. So that will be depending on VREF voltage. So as you notice here, if the voltage, I mean, in here, it's very clear that, you know, representation is not very good, you know, if the bit number is not high. Okay, so this is like 2-bit representation, this is 3-bit representation. Okay, so and then the signal that we say here, for example, is going to be maybe represented with a different number. I mean, this signal here is represented with this, so there's an error here. Okay, so for this one, it's good. It's exactly the same, but you know, there's going to be always an error in these representations. So again, for simplicity, I mean, we call that error quantization error. Okay, so this is, you cannot escape from this error. And this error will be depending on your resolution, bit resolution. Okay. So if you have, let's say, 3-bit converter, and then let's say the full scale is for convenience selected as 8 volt, so it's easier for us to understand. So voltage of the least significant bit voltage contribution is going to be the full scale divided by 2 to the power n. So that's going to be 8 volt divided by 2 to the power 3. So it's going to be 1 volt. Okay. So there is this device, analog to digital converter, and then we ask that device to make a decision. Like, you know, if the voltage is 0, input voltage. Okay, so if the input voltage is 0 volt, okay, let's say this is voltage. Now what we will be doing is we will call this thing as the V in, and we will call this thing as V out. Okay, so the device, I mean, is going to be, maybe you will be giving a pure nice sine wave here, but here there's going to be a representation like this, okay, of that signal. So for 3-bit, of course, this is going to be maybe 8 kind of steps. So what happens is, of course, ideally for a signal, We prefer to have an ideal, I don't know if this is nicely drawn, but not nicely drawn. Okay, this is better, yes. Let me do this one more time. Okay, looks better maybe. Now, ideal, I mean, if the input is, 0, output should be 0. If the input is 0.1, output should be 0.1. That's what we expect. But if you have 3-bit representation, this is not going to be really the case, because here, if your, let's say, this is going to be how the response is going to be. I mean, up to here, this is how this depends on how you make that transition critical thing is between 0 up to 1 volt. This is going to be called as 0, 0, 0. So at the output of the digital to analog converter, the output is going to be 0. So so quantization error as definition is equal to V ideal minus V actual. Okay. So in the actual case, this is going to be actual. So this is going to be digital representation 0, 0, 1. And this is going to be in between 0, 1, 0. Okay, so if this is now is 0, 0, 1, then in the D to A converter is going to be showing it at the output like this. And then until it goes here, it will be remaining in there, and then it will go up. Okay, so in here, if the input was, let's say, 0.5 volt, then the mistake here in the quantization is going to be 0.5 volt. So basically, we can write that amount, 0.5 volt is half of the LSB. So, half of the LSB. So the error is going to be 0 for input is 0, but error is going to go up to here when it is, let's say, the voltage is 0.99. Okay, so there is going to be this much mistake during the transition or conversion. So again, when it goes here, it's going to be nicely, selected value, but then you will see again a mistake. Okay, so there's going to be an error. Ideal output and actual output is going to be different than each other. Okay, so V out actual here. So in summary, I mean, in all these representations, this is how the actual result is going to be. Let's say this 8 volt, okay. So this is actual output and actual analog output. So, I mean, this is inevitable mistake, of course. Okay. And maybe I should throw one more. And, you know, remember that this voltage is LSB voltage. So the maximum error is here, VLSB. Of course, if N goes up, then VLSB is going to be reduced. Okay, so that is the concept. Is that clear? So, you know, this mistake here, 1 LSB is the maximum deviation from the voltage. But I mean, with a simple trick, we can, you know, reduce this error if we make that switching maybe at the half of that voltage. So we can say that this is going to be 0 volt, right, at the output, but this is 0, 0, 0. But when it comes to 0.5 volt here, we say this should be switching to maybe 111. Oops. When it goes to here, this is going to be 111. You know, 111 goes back to 1 volt. So this will be switching here, the actual. And then up to here, it will be staying, and then just about 1.5 volts, it goes to here, okay? So if we do this, switching at the midpoint, then this will be slightly better. Why? I mean, let's draw the actual graph. This is the actual what we want. So why is it better? Because if you look at the difference here, let's now draw this difference. You know, up to here, there's going to be a mistake. And then, you know, just about, let's say 0.51, then this is going to be showing as 111. But in actual, it's supposed to be 0.5. So there is going to be a mistake of, you know, 0.5 here. So this is going to be 0.5, but it's going to be minus 0.5. So If the signal increases, it will be good, you know, coming to here. So no error here, the same, but then it's going to be increasing again. And then it will be decreasing. It will be increasing. It will be decreasing. Now, as you see here, and the error is below half LSB. Okay, so the quantization error now, if the change point are shifted 1/2 voltage of LSB, then quantization error will be between 0.5 LSB and then it's going to be minus 0.5 LSB. Okay, or we can say that quantization error is below 0.5 LSB. Okay, so yeah, there's going to be you know, over value and under value, but it's going to be within a smaller range. So this is better, okay, than the previous one. And then the mistake and error, quantization error is going to be less than 0.5 LSB. Is that clear?
Yes, Hocam.
Okay. So this is the, by the way, this is the ideal case, and the devices that are going to be making this conversion will have also, you know, contributing to this mistake. So this is naturally the ideal. Okay, so this is ideal quantization error, assuming that our A to D is precisely, you know, doing this thing. So we'll see that, you know, there might be some mistakes because let's say we say it should be switching 0.5 volt, but then the analog circuit that we make to make this thing is going to be switching at 0.6 volt by mistake. Okay, so and then we'll see that quantization error is going to be changing. So this is the ideal quantization error. And we'll see how then we will be making some definitions, more definitions of the mistakes. Okay. So let's see, shall we continue or give a short break here? Let's give a short break here, and then we will continue with this converter. So we'll be starting to digital to analog converters first, and then what is going to be the actual case, and how we can implement them is going to be also a subject of this course. We will be seeing basic implementation methods. So what is inside? Okay, so inside of this will be discussed. So let me give a break, maybe 5 minutes break. Okay, so at 46 we can meet. Okay.
Ya bir şey sorabilir miyim? Bu az önceki implementation yapmamız için bizim 9 tane level'e ihtiyacımız olmuyor mu? 3 bitte nasıl yapıyoruz onu? 0'dan 8'e kadar.
Okay, I think after this hour it will be more clear. You know, there's going to be, of course, a mistake here. So I think let me explain this one. Maybe it's going to be better, you know, and clear. Okay. So, you know, it's easier to understand or how to implement digital to analog converter, and also digital to analog converter sometimes is used to make an analog to digital converter. So it's better to start from digital to analog converter concept. So in this concept, as you know, the input data, the binary data, is going to be entered like this. Maybe we should have set here, you know, an minus 1, a0. Okay, so it's maybe not so good to mention about this. So if the signal or input to here, you know, is 0, 0, 0, let's say we enter here 0, 0, 0, okay? So then there's going to be reference voltage, and then output is going to be generated. So the generated output is going to be, if the input is 0, 0, 0, the output is going to be 0. So output will be 0. So this is in terms of voltage. This is binary input. Binary input. So this device is going to give you 1 volt. If the input is like this, it's going to give you 2 volts. Again, for convenience, we selected the full scale to be 8 volts and then 3-bit DAC. Of course, if the full scale is 4 volt, then 3-bit DAC, this is going to be 0.5 volt, right, instead of 1 volt, but this is more convenient. So the device itself is going to give us a voltage like this. So there's nothing in between, you know, either the input is 0, 0, 0 or 0, 0, 1. So the output is going to be like this. So V least significant bit is equal to V full scale divided by 2 to the power n. where 8 volt and then 2 to the power 3 is going to be 1 volt. So each step, going from here to here is least significant with voltage, which is 1 volt. Okay. So what is the voltage of the most significant bit? Again, this time, this is going to be V LSB times 2 to the power n minus 1 is going to be the most significant bit. For this case, it's going to be 1 volt times 2 to the power 2, which is going to be 4 volt. Okay, so this is how we understand. And then they determine the value. So as you see here, for example, this one, which is most significant bit is 1, the others are 0. Representation or corresponding voltage is going to be 4. Okay. So what is the maximum voltage here? When this one, the maximum voltage is going to be 7 volt. Okay. So as your friend pointed out, if we are going to represent the voltage from 0 to 8 volt like this, then I mean 3-bit will not be enough, but that's what we do, and then it creates a problem. I mean, it creates an error. So at the output, the maximum output is going to be equal to 7 volt, not 8 volt. So 111 is the maximum we can write with 3 bits, and that will be corresponding to 8 volt. Okay, this will be corresponding to 7 volt, sorry. Now this is the D to A, not A to D. Okay, so here we made the reference voltage we apply, and that reference voltage is typically is considered as the full scale, and then that voltage for this case is 8 volt, and then that's how we represent. Okay, is that clear now? We don't get 8 volts at the output. And that is our actually quantization error. That's our error. We accept that. So we are, in fact, lucky if this is the case. Because, how are we going to implement this? This is going to be implemented with maybe resistors and transistors, some other components. But if those components are ideal, this is what we will be getting as the output. Okay, so this is going to be ideal response. I mean, ideal response, it's not the ideal, I mean, but ideal response of the duck. Okay. Of course, ideally, it is not representing our signal nicely. So the signal that we obtain, and then the outputs are going to be ideally like this, right? I mean, like let's say 100 needs to be giving us 4 volt. But this device, the duck, might give a signal like this. Okay, so the output, for example, for 000, it's not going to be 0 volt, but output is going to be maybe 0.9 volt. okay? 0.9 volt or 0.8 volt, I don't know. Let's say 0.8 volt, okay? So, but if each case the output is shifted 0.8 volt, this is okay. I mean, we like this also, you know, this is not bad. Then we will say that the offset is going to be 0.8 volt, and then we can subtract from the output all that voltages. We put an extra circuitry and then subtract that 0.8 volt, and then it will be corrected. Okay, so this thing can be corrected easily. Okay, another problem we might have is that the signal is going to be giving us like this. So the slope that we see here, okay, so this is not a big deal. The output can be corrected easily. Okay. So scale factor, this is called the scale factor error. So the voltage is going maybe, you know, in a nicely increasing format, but then the amount of the output voltage is less. So that's called scale factor error. Okay. Again, not a big deal. What can you do? You know, just put an amplifier. With an amplifier. Voltage amplifier easily by subtracting the offset. Okay, so the problem in fact occurs if this is the case. I mean, if let's say the signal for this one gives us 0, okay, for this one it gives 0, but for this one maybe I should do this. So if this is the input, then the output becomes like that. If this is the input, output goes back to correct one. But this one, it goes up, and then sometimes it goes down. Okay, for this case, it goes down, and then so it goes up and down. So it's called nonlinearity, and then this is a big problem. Okay, cannot be corrected. Okay, so and then we need to, just know that, and there are definitions like how we can define and deal with that. We just need to maybe characterize the output voltage and then come up with an error. Okay, so we'll be, hold on a second. If the, some example is given here. If the signal is 0, 0 as the input binary, and output now is good, nicely measured as 0 volt. Okay, so the actual voltage is 0. That's supposed to be 0. So there is no error here. Okay. The the integral, linearity error is defined as this one is defined as actual output minus ideal output divided by voltage of LSB. So here, for this circuit, LSB is 1 volt. So this is easier for us to maybe calculate. VLSB is 1 volt, right? So this is 8 volt divided by 2 to the power 3. So this was full scale, right? So that is the case. So integral nonlinearity error here is going to be 0 voltage. That means 0 LSB. Now, the next bit, which we say is going to be 001, let's say it comes out as 0.5 volts. So ideally, we expect this to be 1 volt, but it comes out to be 0.5 volt. So integral linearity error is going to be how much? Actual minus this one. So this is going to be minus 0.5 volts, which is going to be 0.5 LSB, minus 0.5 LSB. Okay, so I guess you understand it right now. Here it's supposed to be 2 volts, and then it is 2 volts. So the mistake is 0 volt. That means the mistake is 0 LSB. Okay. So we can calculate here. It gives 3.5 volts. It's supposed to be 3 volts. So this is going to be plus 0.5 volts. Therefore, it's going to be 0.5 LSB. The mistake. Okay, the mistakes is written in terms of LSB. So here it's going to be 0.5. This is going to be minus 0.5. Why? This is because less. It doesn't have to be going with this precision. It can be 0.4, 0.2. But for, I guess, simplicity, it's given like this here. For 6 volt, it is correct. So this is 0. And then for 7 volt, it is 7.5. So this is going to be 0.5. So this integral nonlinearity error is defined in terms of defined in LSB for convenience. Okay. So this is 0.5 LSB. Okay. So, but there's another error one. It is about the step. This one, differential linearity error, is an error caused by the step. Here differentially we look at the issue. Okay. So this one is called step size in LSB. Actual step size minus 1. Okay, so is the definition. Okay, so here let's look at the case. Hold on a second. So the thing here is it is supposed to be going one step up, right? So this is now shorter than that. And we expect the signal to be going 1 LSB up, but it is 0.5 LSB less. So step size is how much it increases here. So this is the step size, step. So step size is, maybe I should give the definition here. Step size is the actual output minus actual previous output divided by VLSB. Okay, so here, I mean, from this output voltage, it goes to this output voltage. Okay, so step size. Step size compared to the first one is now what? 1.5 step. But normally, you know, from this bit, we just increase 1 bit and then it goes a voltage of 1.5 bit. Then we call this thing as a mistake again. Even though compared to actual, it is correct. I mean, this is correct. In terms of internal linearity error, okay, so is equal to 0. But this step size is equal to 1.5. So step size is more than 1 LSB. So is mistake. Okay. So this is how we look at the mistakes. From here to here, the jump is 1.5 volt. That means 1.5 LSB. Here to here, it is 1.5 volt. So this is going to be again 0.5. Here to here, I mean, this step is 1 volt. So there is no mistake here. From here to here, what is that? 5 volt, 4.5 volt. Wow. There's -1. No change. And here to here, it is 0.5, and then from here to here plus 0.5. Okay, so this is not defined for the first bit. That's how we define the errors here. So and the errors are here. Two different errors. Is that clear? You know, why does this happen here? I don't know. The circuit has a mistake. I mean, the circuit that we try to implement has a mistake. So it doesn't change anything here to here, even though one bit is increased. Okay. So these are just the definitions, and for convenience, we gave 8 volt and 3 bits, and then 1 volt LSB, so that it's going to be, you know, clear. So this is also written in LSB. Okay, the significant bit or bit, how much error there's a bit here. So I guess if we start seeing like how these things are implemented, maybe it's going to be more clear where these errors are coming from. Okay, so this is the most straightforward implementation of this device. You know, we say that this is going to be D to A converter. And then there's going to be 3 input bits. And we enter here V reference. And then there's going to be V output. Output voltage will be happening here. Okay, so this is N bit. N bit signal. So maybe I should say here like 0, 1. Oh, sorry. N minus 1. So this is the circuit, and let's say we try to create a voltage here. Okay, so the voltage that we want, remember, V out needs to be created, right? So we say that V out is supposed to be ideally V full scale times, depending on the representation, A n minus 1 divided by 2. 2 to the power n times 2 to the power n minus 1. plus A0 to the power n times A0 times 2 to the power 1 to the power 0, sorry. Okay, so either we write it this way, or we can write it this as V full scale, depending on the condition of this. This could be 1 or 0, but the voltage is going to be divided by 2, A n minus 2. The voltage is going to be equal to 4, and then A0, the voltage is going to be 2 to the power n. Okay, so let's say this is how, we represent. So if the signal is 1 0 0 0 0 0 0, then V out is going to be V full scale times 1 over 2, and others are going to be 0 over something. Okay, so output is going to be V full scale divided by 2. So representing to this is going to be like that. If the signal is 0 0 0 and then 1, then V out is going to be equal to V full scale divided by 2 to the power n. Okay, here, that's what we want to implement. And the way that we implement is with the switches, okay? So, in this circuit, let's say this is the way the switches work. Vn, let's say anytime. If it is 0, Vn minus 1 maybe. If the signal is 0, then this switch is connected to ground. If this one is 1, it's connected to full scale. So what? I think there's something wrong here. The way they defined 1, 2, 3 is, well, I guess for convenience, they switched the representation, but this will be the most significant bit. So there's a mistake here. I guess they switched. I mean, the nodes are such that they write it like B1, B2, B3, Bn, but B1 is equal to an minus 1. Okay, and then the Bn means A0. Okay, so this is the most significant bit, and then this is the significant bit for this case. Okay, so so what happens? I mean, if you have a circuit like this is just an adder, as you know. Let's say Bn, which is least significant bit now. Okay, so and it has a resistance of 2 to the power n r, and this is an r. Okay, so there's going to be current coming from here, and then since it's an ideal op amp, the current is going to be 0, and then there's going to be current going to be 0, and the currents that added up here is going to be going through here, and then V out is going to be obtained. So V out is going to be equal to, maybe I should use another color here. V out voltage is going to be equal to 0 minus, because this voltage is 0, 0 minus R times I n plus or R1 I1 plus I2 plus IN. Okay, all the currents coming from those bits are going to be added up. And what is I1? I1 is going to be conditionally, I1 is going to be this current, is going to be conditionally B1, value of B1 times V full scale divided by 2R. Correct? I mean, if this B1 is connected to 0, or B1 is 0, then it's connected to ground. And how much current is going to be coming? 0 current. No current comes in here. Why? Because this is 0 volt, and then if the other side is 0, no current is coming. So it's conditional. Plus V2 times V full scale divided by 2 to the power 2R. What about this last one? This one. Bn times V full scale divided by 2 to the power n. So, all these currents are added here. I total, and that current goes to R, and then voltage is created. So in fact, then V out will be equal to minus R times V full scale times B1 divided by, maybe I can take the R to the outside also. right? If I take the output as the R divided by R, so this is going to be 2 plus B2 divided by 2 to the power 2 plus Bn divided by 2 to the power n. That's it. This is what we have here. I mean, thinking that, you know, this is representation is donation, I mean, is switched. So this will be gone. So we have V out to be minus V full scale times, right? It was plus here, but this time it's minus. So we can select the full scale to be, I mean, V minus Vref, V full scale. This is supposed to be Vref, in fact, you know. But anyway, let's not confuse that. Times, what was B1? A n minus 1 divided by 2 plus A n minus 2 divided by 4 plus A 0 divided by 2 to the power n. Okay? So this is it. This is how we can, you know, write this thing. So you can select the voltage to be minus 8 volt, for example. Okay, so this could be, you know, selected to be negative. So then, you know, we have a converter. Is that clear? So, like if you, for 3-bit, I mean, for the previous case, this can be. So then the output voltage is going to be positive. This is how we can implement digital to analog converter. This is very easy in a sense, and that's what we end up getting. I hope this is clear, and I'm going to stop here. We will be seeing maybe some other versions of this, how we can do that. So the mistakes that we were talking about is maybe related with these resistances. So let's say we select this, one of them, R, is selected as 1 kilo ohm. Okay, so we want this to be for 10-bit, it's supposed to be 1 mega ohm, 1.24 mega ohm. So is it going to be with that precision? So any mistake in those resistances is going to be creating an error. So that error will be causing us these, you know, mistakes here. Okay. So that's the basics for the errors also. But I guess now we have a basic understanding of these converters, and then you have seen the first implementation of digital to analog converter. So you have an idea. So I'll stop here. Let's see, I mean, how we can represent. And how we can see implement the other types.